Alright, so today we'll be dealing with this really huge chapter that's been kind of like a nightmare for everybody, and I think we're gonna ace it together by the end of tonight. So, alright, so let's begin without any further ado. So, how I'm gonna basically do it is I've already got like a partially written notes with important stuff in here. So, as I go through important things, I'm gonna fill it up. Thus, this is what I'm actually going to do. So, alright, without any further ado, let's dive into the chapter. In the earlier chapters, we primarily considered the motion of a single particle. A particle is ideally represented as a point mass having no size. We apply the results of our study even to the motion of bodies of finite size, assuming that motion of such bodies can be described in terms of the motion of a particle. Any real body which we encounter in real daily life has a finite size. In dealing with the motion of extended bodies, often the idealized model of a particle is inadequate. In this chapter, we shall try to go beyond this inadequacy. We shall attempt to build an understanding of motion of extended bodies. An extended body is in first place, it's basically a system of particles. And we shall begin with the consideration of motion of a system as a whole. The center of mass of the system of particles will be the key concept here. We shall discuss the motion of the center of mass of a system of particles and usefulness of this concept in understanding the motion of extended bodies. A large class of problems with extended bodies can be solved by considering them to be rigid bodies. Ideally, a rigid body is a body with a perfectly definite and unchanging shape. The distances between all pairs of the particle of such a body do not change. Alright. It is evident from this definition of a rigid body that no real body is truly rigid, since real bodies deform under the influence of forces. But in many situations, the deformations are negligible. In a number of situations involving bodies, such as wheels, tops, steel, beams, molecules, and planets, on the other hand, we can ignore that they wrap or twist out of shape, bend or vibrate, and treat them as rigid. What kind of motion can a rigid body have? Alright, before we go to this, I think I'm gonna just fill up what's required. I don't think I've written what exactly is a rigid body in here. So let's do that. Oh. I really think about a rigid body they've given in so many different places of the textbook, so that's exactly why I'm doing it again. Alright, moving on. What kind of motion can a rigid body have? Let us try to explore this question by taking some examples of the motion of rigid bodies. Let us begin with a rectangular block sliding down an inclined plane without any sidewise movement. The block is taken as a rigid body. Its motion down the plane is such that all the particles of the body are moving together. That is, they have the same velocity at any instant of time. The rigid body here is in pure translational motion. In pure translation motion, at any instant of time, all particles of the body have same velocity. Next we have, consider now the rolling motion of a solid metallic or rodent cylinder down the same inclined plane. The rigid body in this problem, namely of the cylinder, shifts from the top to the bottom of the inclined plane and thus seems to have translational motion. But as figure 6.2 shows, all its particles are not moving with the same velocity at any instant. The body therefore is not in pure translational motion. Its motion is translational plus something else. Now, in order to understand what that something else is, let us take a rigid body so constrained that it cannot have translation motion. The most common way to constrain a rigid body is that it does not have translation motion is to fix it along a straight line. The only possible motion of this body is rotation. The line or fixed axis about which the body is rotating is known as axis of rotation. If you look around you will come across many examples of rotation about an axis, a ceiling fan, a potter's wheel, a giant wheel in a fair, a merry-go-round, and so on. Let us try to understand what rotation is and what characterizes rotation. Before we go to that, I think I'm just gonna look into the diagrams. Translational sliding motion of a block down an inclined plane. All the particles are of same velocity, same direction, same instant of time. Rolling motion, as you can see, the points are different. They have different velocities. So at P3, they've given it's 0. And here you can see rotation about a fixed axis, a ceiling fan, and a potter's wheel. Alright, we have everything that we learned about in here. So I think there's nothing else to do. Let's move on to the next part. In rotation of a rigid body about a fixed axis, every particle of the body moves in a circle which lies in the plane perpendicular to the axis and has its center on the axis. So as you can understand, basically they're telling that if you consider a perpendicular axis through the center of mass or something, and every other particle which is horizontal to that center also moves in circular motion. So that's exactly what they're trying. And you can see that very well in the diagram exactly what they're saying. So if you consider points P1 and P2, so if you're rotating the body, those will also rotate in a circular motion. For figure 6.4 shows a rotational motion of a rigid body about a fixed axis, which is the z-axis of the frame of reference. Let P1 be the particle of the rigid body, arbitrarily chosen at a distance r1 from the fixed axis, and the particle P1 describes a circle of radius r1 with its center C1 on the fixed axis. The circle lies in a plane perpendicular to the axis, and the figure also shows another particle P2 of the rigid body. P2 is at a distance r2 from the fixed axis, and the particle P2 moves in a circle of radius r2 and with center C2 on the axis. This circle 2 lies in a plane perpendicular to the axis. Note that the circles described by P1 and P2 may lie in different planes. Both these planes, however, are perpendicular to the fixed axis. For any particle on the axis P3, r will be 0. Any such particle remains stationary while the body rotates, and this is expected since the axis of rotation is fixed. Yeah, so basically we have to remember just one point, that axis of rotation is fixed. Alright, now in some examples of rotation, however, the axis may not be fixed. We did learn about how axis is fixed and there is no, the particle in it isn't stationary, basically stationary, but there are cases where it may or may not be fixed. So a prominent example of this kind of rotation is a spinning top. In place, we assume that the top does not slip from place to place and so does have translational motion. We know from experience that the axis of such a spinning top moves around the vertical through its point of contact. There is point of contact with the ground, sweeping out a cone as shown. So the top around the vertical is termed this moment of the axis of the top around the vertical is known as precession, and the point of contact with the ground is fixed. The axis of rotation at the top at any instant passes through the point of contact. Another symbol of this kind of rotation is the oscillating table fan or pedestal. Alright, pedestal fan. Okay. You may have observed that axis of rotation of such a fan has an oscillating sidewise moment in the horizontal plane about the vertical through the point at which the axis is pivoted. While the fan rotates and its axis moves sideways, this point is fixed. Thus, in more general cases of rotation, such as the rotation of a top or pedestal fan, one point and not line is fixed. In this case, the axis is not fixed, though it always passes through the fixed point. In our study, however, we mostly deal with similar and special case of rotation in which one line, which is the axis itself, is fixed. Alright, so let's quickly check. Alright, yeah. Alright, so I think we've covered most of this part. Let's move to the next one. Okay, so let's see what they've given here. The rolling motion of a cylinder down an inclined plane is a combination of rotation about a fixed axis and translation. Thus, the something else in the case of rolling motion, which we referred to earlier, is rotational motion. You will find figure 6.6a and b instructive from this point of view. Both these figures show motion of the same body along identical translational trajectory. In one case, the motion is pure translational. In the other case, it is combination of translation and rotation. So, we now recapitulate the most important observation of the present section. The motion of a rigid body which is not pivoted or fixed in some way is either a pure translational or a combination of translational and rotational. The motion of a rigid body which is pivoted or fixed in some way is rotation. Right? The rotation will be about an axis that is fixed or moving, and we shall in this present chapter consider rotation motion of a fixed axis. Alright, that is alright now. Let me quickly check on these two. This is motion of a body which is pure translation. This motion of a rigid body which is combination of translation and rotation. I think the best example for this could be the planets, because for the second one definitely, because it's like translation as well as rotation. And translational doesn't just mean it's going in a straight line. So you can see in that diagram, so it's like going in a curved path, so it it can be told it's translation, right? And there's something else I've given in this small paragraph that's here. Let's see what that is. Illustrate different motions of the same body. Note that P is an arbitrary point on the body. O is the center of mass of the body, which is defined in the next section. Suffice to say here that the trajectories of O are the translational trajectories TR1, TR2 of the body. The positions O and P are three different instants of time are shown. Alright. O1 and O2 and O3 and P1, P2, P3 respectively in both the cases are seen from at any instant the velocity of any particles like O, P of the body are the same in pure translation. And notice in this case orientation of OP, that is the angle OP makes with the fixed direction, say the horizontal, remains the same. Now moving on to the next one, it illustrates a case of combination of translation and rotation, and in this case at any instant the velocities of O and P differ. Okay. Also alpha 1, alpha 2, alpha 3 may be different. Alright, so I think the angle makes it pretty important. Alright. Let's see what I've written. I've completely not done that part. Okay, I've put here. So there's more that they've given in that part, which I want to include in my diagram. Alright, we're going strong now. Let's move on to center of mass. I'll just come back after some time, if it gives me some time, so that I can go charge my phone. We're back. So let's learn about the center of mass. We shall first see what the center of mass of a system of particles is and then discuss its significance. For simplicity, we shall start with the two system particle. We shall take the line joining the two particles to be in the x-axis. So as you can see, there's m1, m2. If taken both the particles on x-axis, the distance is basically from the origin. Remember, it's not between them, but it's from the origin. And the distance of the central mass from the origin is also given, alright. Let the distances of the two particles be x1 and x2 respectively from some origin. Let m1 and m2 be respectively the masses of the two particles. And the center of mass of the system is this. Oops, 1 second. Okay. And the x can be regarded as the mass of x1, x2 if the two particles have the same mass. m1 is equal to m2 is equal to m, then you could write it directly x1 plus x2 divided by 2. Alright. Thus, for two particles of equal mass, the center of mass lies exactly midway between them. If we have n particles, then we could use this formula and we could use a summation, alright. And for different coordinates, like for x and y axis, you can use different formulas, and that's also fine. And again, for number of particles lying, not necessarily lying in a plane but distributed in a space, you could use summation. And so here, as you can see, there is something called position vectors. Let Ri be the position vector of the I particles and capital R be the position vector of the center of mass, and the sum of the right hand side is a vector sum. Note the economy of expressions we achieve by use of vectors. If the origin of the frame of reference is chosen to be center of mass, then the summation of MIRA should be equal to 0 for the given system of particles. And a rigid body such as a meter stick or a flywheel is a system of closely packed particles which are applicable to a rigid body, and the number of particles, atoms or molecules in such a body is so large that it is impossible to carry out the summations over individual particles in these equations. Since the spacing of the particles is small, we treat them as continuous bodies, and for them you are basically going to use integration. So you're going to integrate the whole thing up. Okay, so here is a nice diagram. I do not know if I've seen this before, but it's a nice diagram that can explain how exactly you do the summation. So often we have to calculate the center of mass of homogeneous bodies of regular shape like rings, disks, spheres, or rods. By a homogeneous body, we mean that the body is uniformly distributed mass. By using symmetry consideration, we can easily show that the center of mass of these bodies lie at their geometric center. So they've considered a thin rod whose width and breadth, in case the cross section of the rod is rectangular or radius, is much smaller than its length, taking the origin to be at the geometric center of the rod and x-axis to be along the length of the rod, we can say that on account of reflection symmetry for every element dm of the rod at x, there is an element of the same mass dm located in minus x. The net contribution of every such pair to the integral and hence the integration of xdm itself is 0. From, okay, I think this is one point that is pretty important. Alright. Itself is 0 is the center of mass. Thus, the center of mass of homogeneous thin rod coincides with its geometric center, and this can be understood on the basis of reflection symmetry. They use this new word called reflection symmetry, and I'm pretty sure we shouldn't be new to it. The same symmetry argument will apply to homogeneous rings, disks, spheres, or even thick rods of circular or rectangular cross section. For all such bodies, you will realize that for every element dm at a point x, y, z, one can always take an element of the same mass at the point minus x, minus y, and minus z. As a result, the integrals are all are 0. This means that all the above bodies, their center of mass coincide with the geometric center. Okay, so next I've given a question. I think we've done this, so I'm gonna skip it for now. And yeah, there's a question here. Find the center of mass of a triangular lamina. So when it's a lamina, it means it's like a 2D kind of a plane, and it's a triangle of LMN. Now they're telling us basically to find the center of mass. Now, how do you find the geometric center of a lamina? It would most likely be the point of intersection of their medians. So that's exactly what they've done. Now there is something new that they've inculcated in here. If you might ask what exactly that is. Now let's say they've considered this whole lamina to be divided into narrow thin strips, and each strip is parallel to the other. By symmetry, each strip has a center of mass at its midpoint. If we join the midpoint of all the strips, we get the median. The center of mass of the triangle as a whole, therefore, has to lie on the median LP. Similarly, we can argue that it lies on the median MQ or on NR. Okay, so there's one doubt I'm getting is like if we consider, alright, never mind, we can do that. Okay, since this means the center of mass lies on the point concurrence of the medians, that is on the centroid G of the triangle. Alright, next we have a different question, which is find the center of mass of a uniform L-shaped lamina, which is a thick flat plate with dimensions as shown, and mass of the lamina is 3 kg. Choosing X, okay, fine. They've given a L-shaped lamina with dimensions, and we need to find mass of lamina. Okay, mass is also given. We should find the center of mass. Okay. It's a pretty important question. I've seen like past questions from here. Okay, first let's try it ourselves and then let's check it with the answer, shall we? Now, for every square, the center of mass is definitely this. But for the whole thing, what would be the center of mass? Okay, as far as I've learned, I definitely know that D is, but how do you find that out is one thing that's supposing me. Okay, so let's try the M method. Hmm? So they've given mass of lamina is 3 kg. Then whatever each side, do we take it as unit or okay, so let me just quickly go through it. Choosing x and y as shown, we have coordinates of the vertices L shaped lamina as shown. We can think of the L shape to consist of 3 squares each of length of 1 meter and mass of 1 kg. Okay, they've literally considered it themselves. This is something I am weak at because I don't know what to consider when. But now that we've learned it, I'm pretty sure we can do that in any other questions. So let's consider an L shape, consider the unit length of each squares, that there are 3 squares, and then you will just consider since whole lamina is 3 kg, since all these 3 squares are equally divided, let's consider each square to have 1 kg. Alright, centers of mass C1, C2 and C3 of the squares are by symmetry their geometric centers and have coordinates so and so and so. We take the masses of the squares to be concentrated at these points. And center of mass of the whole L shape would be xy. And now we put the formula. Okay, now that we put the formula, I think it's gonna be pretty easy, because once you know the coordinates and once you know the mass, you can directly put it in the formula and find an answer. The center of mass lies at the line OD. Where is O? Okay, origin. We could have guessed this without calculation. um Yeah, so there are two important questions. Firstly, they've asked we could guess it with a calculation. How, if you might ask, it could be due to geometric center, as all of them have unit masses. And if they're asking what if the masses are different, they're not unit. Well, according to me, the center of mass would be closer to the body which has the heaviest weight. So that's my point of view, and I think we are done with this section. Quickly gonna check out how is my notes. Alright, we're pretty clear with this. I've written everything that's required. Let's see our progress. 1, 2, 3, 4, 5, 6, 7. Finish 7 pages, so we have 7 more and we'll be done with half of the chapter. Okay, that sounds interesting. Let's quickly move on. I think I'm just gonna see a little bit of all this. Cool. I think this one feels more like a revision because I've done this material quite sometimes, and continuous revision can make stuff, stick into my head. So let's go. Equipped with the definition of center of mass, we are now in a position to discuss its physical importance for a system of particles or m particles. So mr is definitely a summation of miri, and differentiating the two sides of the equation with respect to time, we get something like this. Now you know that dr by dt is v, so you could put the whole equation as mv is equal to m1 v1 m2 v2 and also. And v is d, okay, that's something we know already. And definitely masses don't change with time unless they are like a rocket propulsion or something. But so far we've gone with a simple like system of particles, alright. We have therefore treated them as constants in differentiating the equations with respect to time. Differentiating with respect to time, we obtain, okay, once more differentiating it, we'll get dv by dt, so that is A, acceleration. So you do the whole thing, they've again told the same thing. Now, a plot twist. You know what ma is? Mass into acceleration. So you could have the whole equation for force too. That is pretty smart and simple. Thus, the total mass of a system of particles times the acceleration of its center of mass is the vector sum of all the forces acting on the system of particles. Note that when we talk of the force F1 on the first particle, it is not a single force, but the vector sum of all the forces acting on the first particle. Likewise, for the second particle, among these forces on each particle, there will be an external force exerted by bodies outside the system and also internal force exerted by the particles on one another. Yeah, because it's accelerating, right? So there will be external forces. But also they're telling there will be internal forces too. Alright, we know from Newton's third law that these internal forces occur in equal and opposite pairs and in the sum of forces. So this is the action and reaction forces and their contribution is usually zero. Only the external forces contribute to the equation. Therefore, we can write it as ma is equal to F external. The F external represents the sum of all external forces acting on the particles of the system. So next we have, oops, one second. Yeah, the center of mass of a system of particles moves as if all the mass of the system was concentrated at the center of mass and all the external forces were applied at that point. Remember this point. Notice to determine the motion of the center of mass, no knowledge of internal forces of the system of particles is required. For this purpose, we need to know only the external forces. To obtain equation 6.11, we do not need to specify the nature of the system of particles. The system may be a collection of particles in which there may be all kinds of internal motion, or it may be a rigid body which has either pure translational motion or a combination of translational rotation. Whatever is the system and the mass of its individual particle, the center of mass moves according to equation 6.11. Remember that is the motion of center of mass, F external is equal to ma. Instead of treating extended bodies as a single particle, as we have done in earlier chapters, we can now treat them as system of particles. We can obtain the translational component of that motion, that is the motion of center of mass of system, by taking the mass of the whole system to be concentrated at the center of mass. So basically it's like a relation. You so far considered for a point particle. Why? Because you consider it doesn't have mass, it's not an extended body, it's a very tiny point particle. But now how it relates and makes things easier is even an extended body you're considering the point particle because you're assuming that all the mass is concentrated in the center, and that's exactly how gravity acts too. Like let's take a ball. You've seen people balancing ball with a finger, right? So that how does it happen? Like how can that balancing happen? It's basically center of mass, and that makes things easier, and it's not just a theory, but it's what real physics is. So yeah, I don't want to go into philosophy right now. Okay, so this is a procedure that we followed earlier in analyzing forces and bodies and solving problems without explicitly outlining and justifying the procedure. We now realize that in earlier studies, we assumed without saying so the rotational motion or internal motion of the particles were either absent or negligible. We no longer need to use this. We have not only found the justification for the procedure we followed earlier, but we also found how to describe and separate the translational motion in a rigid body which may be rotating, as well as system of particles with all kinds of internal motion. So let's see this amazing diagram. It's a good illustration of equation 6.11. So what did we learn in equation 6.11? It's basically center of mass into, okay, the weight of the center of mass into acceleration is equal to force external. A projectile following the usual parabolic trajectory explodes into fragments midway in the air. The forces leading to the explosion are internal forces. Alright, because of internal chemical reaction, there's an explosion, let's say that. They contribute nothing to the motion of the center of mass. The total external force, namely the force of gravity acting on the body, is the same before and after the explosion, and the center of mass under the influence of the external forces continues therefore along the same parabolic trajectory as it would have followed if there were no explosion. That's something very important, and I've seen them asking like very simple questions on it. So all you have to remember is that the center of mass continues in the same direction even though the fragments have like blasted away. And yeah, that's so much it about it. And the external force acting on it would be force of gravity. So if you see the diagram they've given in y-axis like they've given parabolic path of the projectile and path of the center of mass of fragments, which is again the same even if it are not blasted. So that is something we've learned here. Let's see how I've written that part as. I've written an extra thing, but we'll come back. Okay, I've written it. Cool. Okay. What do we have next? I assume it's linear momentum, or is it angular momentum since we're dealing with. Okay. Linear momentum of a system of particles. Let us recall that the linear momentum of a particle is defined as P is equal to mv. Let us also recall that Newton's second law, written in a symbolic form of a single particle, is F is equal to dp by dt, where F is a force in the particle, and let us consider a system of n particles with masses m1, m2, mn respectively and velocities v1, v2 until vn. The particles may be interacting and have external forces acting on them, and the linear momentum of the first particle is m1 v1, of the second particle is m2 v2, and so on. For the system of n particles, the linear momentum of the particle is defined to be vector sum of all the individual particles of the system. So as you can see here, and p is equal to mv. The total momentum of a system of particles is equal to the product of total mass of the system and velocity of its center of mass. Now let's say we differentiate that. dp by dt is F external, and you get back the equation ma. So this is a statement of Newton's second law of motion extended to a system of particles. So in Newton's second law, you learn that change in momentum is force, and like force is mass and acceleration. So that's exactly what's happening in here, even when there is a system of particles. Suppose now that the sum of external forces acting on a system of particle is 0. dp by dt is 0 and p is constant. Thus, when the total external force acting on a system of particle is 0, the total linear momentum of the system is constant. This is so unsimilar to what we have learned in laws of motion. It's like a continuation, it's like a revision. And okay, because of equation 6.15, what is equation 6.15? Okay, I've seen it. This also means that when the total external force in the system is 0, the velocity of the center of mass remains constant. We assume throughout the discussion of system of particles in this chapter that the total mass of the system remains constant. Yeah, that's important. Note that on account of internal forces, that is, forces exerted by particles on one another, the individual particles may have complicated trajectories, yet if the total external force acting on the system is 0, the center of mass moves with a constant velocity, that is, moves uniformly in a straight line like a free particle. And the vector equation 6.18a is equivalent to 3 scalar equation. Okay, right. And they've given 2 examples, I believe, of these. Okay. As an example, let us consider the radioactive decay of a moving unstable particle like the nucleus of radium. A radium nucleus disintegrates into a nucleus of radon and alpha particle. There's something we need to know: radium to radon and alpha particle. The forces leading to the decay are internal to the system, and the external forces in the system are negligible. So the total linear momentum of the system is the same before and after decay. The two particles produced in the decay, the radon nucleus and the alpha particle, move in different directions in such a way that the center of mass moves along the same path along which the original decaying radium nucleus was moving in. If you observe the decay from the frame of reference in which the center of mass is at rest, the motion of the particles involved in the decay looks particularly simple. The product move back to back with their center of mass remaining at rest as shown. In many problems on the system of particles, as in the above radioactive decay, it is convenient to work in the center of mass frame rather than the laboratory frame of reference. So, as you can see, it's basically like shown in the B diagram what they mean by seeing in a center of mass frame. In the first case, it's like the center of mass is in uniform motion. And in the second case, the center of mass is basically at rest. And that's how the diagram looks like. And it seems... Okay, I kind of get it. So let's see the diagram once more. Alright, I think that's pretty clear. Now let's move on to the next one. In astronomy, binary or double stars is a common occurrence. If there are no external forces, the center of mass of the double star moves to like a free particle. The trajectory of the two stars of equal mass are also shown in the figure. They look complicated, but if we go to the center of mass frame, then we find that these two stars are moving in a circle about the center of mass, which is at rest. Note that the position of the stars have to be diametrically opposite to each other. Thus, in our frame of reference, the trajectories of the stars are a combination of uniform motion in a straight line of the center of mass, circular orbits of the stars about the center of mass. As can be seen from two examples, separating the motion of different parts of the system into motion of center of mass and motion about the center of mass. Okay, look how important that sounds. Separating the motion of different parts of the system into motion of the center of mass and motion about the center of mass is a very useful technique. I think that's something worth writing there. Yeah, written it here. So next we have a pretty easy concept. I think we can stretch a bit right now. Alright, so this is about vector product of two vectors. We are already familiar with vectors and their use in physics. In chapter 5, work, energy, power, we defined the scalar product of two vectors. An important physical quantity, work, is defined as a scalar product of two vectors, which is force and displacement. Okay, so we shall now define another product of two vectors, Now this product is a vector. It's not like always product of two vectors is a scalar, but product of two vectors could be another vector too. Let me remember that, because I would have opted for the wrong option if asked in this way. Where two important quantities in the study of rotational motion, namely moment of force and angular momentum, are defined as vector products. Definition of a vector product. The vector product of two vectors A and B is the vector C, such that C is equal to AB sine theta, and C is perpendicular to the plane containing A and B. If we take a right-handed screw with its head lying in the plane of AB and screw perpendicular to this plane, if we turn the head of the direction from A to B, then the tip of the screw advances in the direction of C. This right-handed screw rule is illustrated in figure 6.5. I think imagining itself made a great sense. Alternately, if one curls up the fingers of right hand around the line perpendicular to the plane of vectors A and B, if the fingers are curled up in the direction from A to B, then the stretched thumb points to the direction of C. I'm pretty sure you guys would have done it with me, because it's exactly how it is supposed to be. Next, a simpler version of the right hand rule is following: open up your right hand palm, curl your fingers pointing from A to B, and then okay. It should be remembered that there are two angles between any two vectors, A and B, in figure 15A, or B, they correspond to theta, and the other is 360 minus theta. While applying either of the above rules, the rotation should be taken through the smaller angle. Okay, that's a point to remember. So it is theta here. Okay. Because of the cross used to denote the vector product, it is also referred to as a cross product. Note that scalar product of two vectors is commutative, but vector product is definitely not. Like, I am pretty sure you guys would have learned about matrices in like 10th or something, and that makes things easier. Like, you could understand that if you've done the vector product wrongly, like the product of two of those matrices wrong, you would end up getting like different answers. Like, it would be same numbers, same magnitude, with a different sign. So that's exactly what happens in vectors too. Now the magnitude of both A cross B and B cross A is the same. Both of them are perpendicular to the plane A and B, but the rotation of right hand screw in case of A and B. Okay, this is exactly what I had told you right now. Another interesting property of a vector product is its behavior under reflection. Under reflection, x would give minus x, y would give minus y, z would give minus z. As a result, all components are able to change sign. And what happens to A cross B under reflection? It does not change. An important thing, something that I forgot, I didn't believe. I'm going to include it. A cross B under reflection. Alright. Next, we have both scalar and vector products are distributed with respect to vector addition, that is A dot B plus C is equal to A dot B plus A dot C, and A cross B plus C is A cross B plus A cross C. We may write C is equal to A cross B in the component form. For this, we first need to obtain some elementary cross products. So A cross A is 0, and 0 is a null vector. that is a vector with zero magnitude. And this follows since magnitude of A cross A is A square sine 0 degree, which is 0. Usually in the scalar one, you will get a unit vector, but here it's 0. And usually in scalar, I cross j would be 0, but here I cross j would give you k. And remember this trick, I suppose. No, so written like this, written like this. So I cross j would give you k, k cross I would give you j. I cross k would give you minus j since you're coming with opposite direction. That's exactly what happens. And remember how to do the vector product helps you. Like, let me show you, okay, a trick of how to do it without messing it up. So always write I cap, j cap, and k cap, and put the first terms here, put the second terms here. And when you're writing the answer, put it like already have this ready, and then you write the answers inside, and then you just learn the answer. That's it. Simple as that. Alright, so now let's go to the next important part, which is angular velocity and its relation with linear velocity. In this section, we shall study what is angular velocity and its role in rotational motion. We have seen that every particle of a rotating body moves in a circle, and the linear velocity of the particle is related to the angular velocity, and the relation between these two quantities involves a vector product, which we learned about in the last section. So let us go back to figure 6.4. Let me see which is that. Let's see. Oh, it's way too front. Okay, got it. I think I've given that again. Yeah, as said above, in the rotational motion of a rigid body about a fixed axis, every particle of the body moves in a circle. We know it, which lies in a plane perpendicular to the axis and has its center on the axis. In figure 6.16, we redraw figure 6.4, showing a typical particle at a point P of the rigid body rotating about a fixed axis, which is taken at the z-axis. The particle describes a circle with the center C on the axis, and the radius of the circle is r, and the perpendicular distance of the point P from the axis. We also show the linear velocity v of the particles at P, and it is along the tangent at P to the circle. And what do we have next? Uh, let's once see the diagram very quick. So that all the z-axis, which is in rotation, and the point P that they've considered has also drawn a circle, and the radius is r, and the velocity is along the tangent of the circle. And after some rotation, if there is an angle formed, then that other point would be P dash, I suppose. Okay, let P dash be the position of the particle after an interval of time delta t. And angle PCP dash describes the angular displacement delta theta of the particle in time delta t. The average angular velocity of the particle over the interval delta t is delta t divided by delta t, as delta t tends to 0. The ratio delta t divided by delta t approaches delta theta, okay, a limit which is the instantaneous angular velocity d theta by dt of the particle at a position p, and we denote the instantaneous angular velocity by omega. We know from our study of circular motion that the magnitude of linear velocity v of the particle moving in a circle is related to the angular velocity of the particle omega, which is v is equal to omega, r omega. R is the radius, and what else is different here? Okay, for particles in the axis, definitely everything is 0. So this also verifies that the axis is fixed. So if by chance you end up getting v is equal to 0 or omega r is 0, let's remember the particular point would be probably in the center of axis. And omega would be the angular velocity of the whole body. And we've characterized pure translation of a body by all parts of the body having the same velocity at any instant of time. Similarly, we may characterize pure rotation by all parts of the body having same angular velocity at any instant of time. Note that this characterization of the rotation of a rigid body about a fixed axis is just another way of saying in a circle which lies in a plane perpendicular to the axis and has a center on the axis. So in our discussion so far, the angular velocity appears to be scalar. In fact, it is a vector. We shall not justify this fact, but we shall accept it. For rotation about a fixed axis, the angular velocity vector always is along the axis of rotation and points out in the direction in which the right-handed screw would advance. Alright. If the head of the right-handed screw rotates with the body, the screw advances in the direction of angular velocity omega. If the sense clockwise and anti-clockwise of the body changes, so the direction of omega also change. Alright, so now we have another diagram. Angular velocity omega is directed along the fixed axis as shown, and linear velocity of the particle v is equal to omega r. Basically, it's v is equal to omega into r. So even if they're given you two vectors, just remember that's how exactly you're basically going to multiply it, and don't mess it up because it's like way too important that v is equal to omega into r and not r omega. And always remember that particular r that we're talking about is basically a perpendicular. The radius is perpendicular to the axis. For rotation about a fixed axis, the direction of the vector omega does not change with time. Its magnitude may, however, change from instant to instant. For the more general rotation, both the magnitude and direction of omega may change from instant to instant. Let's just write some important points. Let me check how much I've done in here. An important one is v is equal to So I'm just gonna put that somewhere like here. So this is equal to omega into r cap. Yeah, I think that's pretty much what we need to know. I'm sure it's definitely different than what I had thought. Let's do a quick diagram. You see this is a particle P and that's TV. Alright. Alright, so we finished half of the section. Not half the number of pages but yet. And this has been an hour, but I still feel it's been pretty long. So I think I might go take some rest and be back.